So my name is Stamat Zabetakis, and on behalf of Cloudera and the Calcite community, I would like to welcome you to today's hybrid meetup event. So let's go over the agenda. So we'll have 4 talks today. Every talk will be around approximately 30 minutes, and there will be a few minutes of Q&A. We'll start with the first 2 talks, and then we'll do a small break of 10 minutes for some snacks and getting some fresh air. And then after the break, we'll do the next 2 talks. And at the end, we'll have some time for open discussion, networking, and socializing. And there will be also some food and drinks so that we can discuss about the presentations or whatever we want. So before moving to the first presentation, Julian Hyde has an announcement to make. So I will invite him on stage. Or you want a mic, or you want to come?
Let me stand. Hello, everyone. Thank you, Stamatis. So yeah, I don't know whether you know me. I'm the original author of Calcite. Currently working for Google. My announcement is I'm leaving Google, and I have no particular place I'm going to next. So the last time I did this was in 2011. My second son had just been born. I decided to leave my job, and I started working on a bit of open source software that was then called Optic and became Calcite. And so I'm in a similar situation that I kind of want to work on something for a few months and just see what happens. So I am planning on working on Calcite, particularly interested in measures in SQL and improving the dialect tests. I'm also working on a language I've invented called Morel, which is a kind of, I think of it as a possible replacement for Spark. So it's a language for writing queries or data-intensive distributed programs. So I'm going to be working on those things, but I'm looking for work. And so if your company is interested in taking on people to do some Calcite projects, let's talk. If you're interested in being a co-founder of like the next big data language, let's talk. If you're a VC and you want to give me money, definitely let's talk. So I'm just saying, I'm putting myself out there, and let's see. And you can reach me through the Calcite dev list or reach me on Blue Sky, all the usual places. I'm going to be working out in the open while I figure out what the next thing is. So thank you.
Thanks, Julian. So now we can pass to the first presentation of the day. So, So for the people who are here, if they want to connect to the Wi-Fi, the name of the Wi-Fi is guest, and the password is written on the whiteboard. So, yeah. So the first presentation of the day will be by Victor Barua, who is going to talk to us about federated query planning with Calcite and Substrate. So I'll stop my sharing and give the mic to Victor.
So my name is Victor Barua, and I'm here to talk about federated query planning with Calcite and Substrate. Who am I? I'm a senior software engineer at Datadog, where I've been working on query optimization and planning for the last 2 years. That's how I kind of first got exposed to both Calcite and Substrate, and as a result of that work, I've become a Substrate management committee member. It's fair to say that I spend a lot of my time looking at trees, turning them into better trees, and then figuring out how to send those trees to other systems so that they can execute those trees. I look at trees a lot. Right off the bat, though, all of these are my own. I'm just here because I want to talk about Substrate and Calcite. In the Substrate community, we've had a lot of folks kind of ask us questions about, okay, how can we use the Substrate library with Calcite to get it to work and do optimizations? And this talk is kind of an answer to those questions from that community. But I'm just kind of here talking about this on my own. I wanted to break down the title of my talk. So, federated query planning with Calcite and Substrate. So Calcite, it's the query planning framework we all know and love. It's very extensible. It's very powerful. And it turns out it's relatively straightforward to get it to kind of do a lot of push down into various systems if you want to do federated queries. And what is a federated query? I imagine there's lots of definitions for it. The definition that I'm kind of going with is that like I might have data across multiple systems, like in Postgres, Elasticsearch, on tables in S3, and maybe some in-house systems. And I want to be able to run queries that can join data across all of the systems. So you might have some executor that's querying all of the systems itself. And at some point, you want to be able to do planning to be like, hey, our user wrote a query that's going to run across 3 different systems. Like, what's the best way to execute that? And then Substrate is a mechanism by which you can kind of exchange plans across those systems. And this talk kind of has 2 audiences. For Calcite folks, I want to kind of let you all know about Substrate. So if you ever think about an exchange format for plans, you might think, oh, that exists. This talk is also aimed at Substrate folks to be like, here's how you can use Calcite. So it's going to be kind of a bridging talk in that sense. That being said, let's talk about Substrate. I've mentioned it a couple of times. So it's intended to be a cross-language serialization for relational algebra. And I think of it as 2 things. One, it's a bunch of protobuf messages. So it's a protobuf encoding of a serialized relational plan. So it's both the messages and also a written spec that tells you, hey, this project relation in Substrate outputs these fields. This filter behaves like this. This function has these output types. So when you combine those 2, you kind of hopefully get self-contained plans that are unambiguously interpretable. But let's kind of dive into Substrate a little bit. I'm going to do like a quick whirlwind tour of it. So like any relational format, you're going to have relations, and you kind of have the standard ones. You've got reads, you've got aggregations, you've got filters, you've got joins, kind of what you'd expect. And then if none of the standard ones work for you, we also have extension relations where you can put in arbitrary protobuf metadata. So we've got standard stuff and then hooks for bringing your own. A relation like the project relation might look like it takes an input, it has 1 or more expressions, pretty standard, If you look at filter, again, pretty similar. It has an input and it has conditions. You've also got stuff like joins, for example, which join take 2 inputs. So you've got a left and a right relation input. It's got the join expression. It's got a type, which can be, again, inner, outer, left, right. This is all pretty boring, right? Like any relational format, you need to have some kind of table scan node. So we've got reads. All reads in Substrate, or all leaf nodes in Substrate, have to fully define their types. And the intent is that a Substrate plan is kind of like fully defined. You don't need to do any schema lookup for a table. It's in the plan already. So in the read rel, we define the base schema. You can also put like filters on it if you want to do like predicate pushdown, best effort filters for like conditional filtering. And then there's various types of reads in the system, like in the default system. So you've got virtual tables if you want to encode like literals in your table and send over the wire. Local files if you want to reference data on disk. Name tables if you want to reference like tables in databases like orders in the TPCH schema. And then something that you may have noticed is all of these relations have this advanced extension field in it. And the advanced extension field, again, is a message where you can put in protobuf any messages to change the behavior of a relation. So if the default behavior doesn't work for you, you can modify it. And as long as you control both the producer and the consumer, you can kind of encode any behavior that you want. And if you don't just want to modify the behavior, you can define your own relations, again, with like extension single rel, which takes an input and a protobuf message of detail. So or a protobuf any message, which again, you can bring your own relations. Cool, so that was relations exhaustively. Now we've got expressions. It's got the things you expect. It's got literals, it's got field references, it's got scalar and window functions. There are also aggregate functions, but they're specifically in aggregate relations. It's got other things you expect like casts. It's got the expressions that you would expect. Guess what? It's also got a type system with kind of standard types like integers, booleans, floats, strings. It's got compound types like structs, lists, and maps. And again, if none of those types work for you, there's user-defined types, so you can bring your own. So what I'm trying to highlight is that there's kind of a core spec of things that we assume that everyone's going to have, but also room for you to bring your own stuff and modify it if your system doesn't quite conform to what we expect. I'm going to skip over the scalar function stuff for now. And then the one thing that's different about function definitions. So in Substrate, the relations expressions are all encoded in protobuf. Functions are in YAML files, and specifically, they're kind of grouped into YAML files based on their functionality. So for example, functions arithmetic has all kinds of numeric functions. So for example, add. In this example, we're declaring 2 variants of add. The first one takes 2 i32 inputs and outputs an i32. The second one takes 2 i64 inputs and outputs an i64. Something about Substrate that's good to know is that if you try to add an i32 and an i64, there's no definition of that function. We don't have any implicit coercion in substrate. Like if you want to do that, you have to like explicitly cast the I32 to the I64. The intent is that by not having kind of implicit coercion, the plans are unambiguously interpretable. We want to make it as easy as possible for you to look at a plan and know what it's going to do, and not have to be like, wait, is it MySQL or is it Postgres doing this, right? Another example of a function is equality, for example, equals, which takes two inputs, again, x and y. And this one we have like the types of those inputs are any1 and any1. And that's kind of like generic. There could be any type as long as those two any's are the same. That was a lot, quite fast, and I could probably talk about this for like 30 minutes if I wanted to, but that's kind of not the purpose of this talk. If you want to learn more, I recommend going to the Substrate website. And also specifically, the SQL to Substrate tutorial will kind of show you how to map a SQL query onto Substrate in like lots of good detail. Okay. Any questions at this point? I think I see someone in the room raising their hand, but I can't tell.
Just a sec. Here you are.
Why is it spelled that way?
Substrate? I don't know. It's a great question, actually.
Other questions? Here online? Good to go, Victor.
Yeah, we'll continue. So, beyond just the protobuf spec, Substrate, the ecosystem also tries to provide libraries for the various languages. So, in Java, we have Substrate Java and Isthmus, which is a module in Substrate Java. And the basic gist of it is this, is that, Substrate the spec just declares the protobufs. And in theory, you could do a lot of manipulations of the protobufs, but I don't know about you, but it's very painful to try and do like visitors and like tree manipulations on protobuf trees. So what Substrate Java provides is like a Java object layer, like a plain old Java object layer, which maps into the Substrate protos and back. And then on the objects, we have nice visitors and like type derivation stuff and kind of a lot of helper utilities to make it easier for you to manipulate the plans. Right? And then as part of Substrate Java as well, we have the Isthmus module, which is how you can convert from Substrate prototypes into Calcite and then back from Calcite into Substrate. So, with the setup, what you can do if you want is you can, configure Calcite as your SQL parser, parse SQL in Calcite, turn it into a rel node, plan it, convert it to Substrate, convert it to protobuf, and then send it out over to the wire to your system. You can also go the other way. And so that's what we do at work, is that we don't actually parse SQL in Calcite. We consume Substrate, protobufs, we convert them to POJAs, we go to Calcite, we do planning, and then we go all the way back. Now, in theory, this diagram is all you need to kind of work a Substrate and Calcite. You've got the conversions, you can go back and forth. But in practice, it turns out like 80% of getting this to work is like knowing the right invocations and various glue, like getting the glue code right. And that kind of motivated the example I'm going to use for this talk, which I'm calling ColorsDB, which is an example federated query planning system. The intent with this is kind of to have a system that you can look at to be like, here is a way of getting Calcite to solve this problem. I don't consider myself to be a Calcite expert. I've been working on it for 2 years, but there's still parts of it that are kind of mystical to me. But I know it well enough to get it to do the things I want it to do, and mostly it works correctly. So what is colors? It's like, well, it's a system made up of 3 data sources, red, green, and blue. And when you combine those colors in the executor, you get, beautiful data. As a motivational example, here's a query that you might want to run. And then the thing I forgot to mention is in colors, I've split TBCH, the schema, across the 3 different colors. So in this query, supplier and parts supplier are in the red system, and then the nation table is in the blue system. And this query is just trying to be like, hey, find me all of the suppliers that have parts with less than 5 availability and show me where they're located, right? Not a particularly like hard query. You can parse it in Calcite, and then with a logical plan where it's like, hey, you've got, 2 red table scans because that data is in red. You join that data, and then you join with the blue table scan because that data is in blue. Apply a filter, and then apply a project. Cool. What we want to be able to do is take that like logical query and turn it into a physical query for execution across all of our systems. So that physical plan might look something like this. We're like, okay, cool. We've still got kind of that blue table scan, and blue is not very simple. I can't do very much. So we just immediately go to like the execution engine in white. in our red table scan, I've actually figured out, oh, actually, we can push the filter into red. So cool, let's push the filter down and then execute it there. And then let's bring it all together in white by joining the data in these two systems in white and applying a project. From here, you can also generate a substrate plan, and I would try to include the plan in the slide, but unfortunately, there's not really a good display format for substrate plans unless you count like a protobuf encoded JSON, which I don't, because that could basically be 50 slides if I needed it. And that example is kind of, I want to be able to do stuff like that. And I'm kind of going to go into some detail about how you can get Calcite to do this a little bit. And one thing to understand before we get through this is kind of like Calcite convention. So if you're a Calcite head, this is probably like not particularly novel, but Calcite kind of keeps track of the convention that nodes are in. The convention kind of indicates where that relation is being executed. So all logical nodes have convention none or logical, which indicates that they are like the platonic ideal of a relation. So logical filter, I want to filter, but I don't know where I'm going to apply it. And in colors, we define 4 conventions: red, green, blue, and white. So 1 for each of the data sources plus the executor. And if a node is in the red convention, it means, hey, this filter, this red filter is going to execute against the red system, or this blue table scan is going to execute against blue. And once you understand that like convention is how Calcite keeps track of like how something is being executed, you kind of have all the pieces you need to know about how to invoke the optimizer to get it to plan for the white convention. You say, hey, give it a logical plan. I want the output, the desired output is that same plan, or I want the, sorry, let me take a step back. That plan has a convention, or has a convention. I want the output of, I want the optimized plan to be the same plan except in the white convention instead of logical. So my desired output is just the traits of the input plan set to white. There's no materializations or empty list to deal with. Just realized there might be questions. Oh, no questions, sorry. There's no materializations or lattices to deal with. And what you can do is say, hey, cool, call it program with my rules. I'm going to go into some of the rules later and say, hey, I want to run the program with the planner that I've created. And in the actual code base, there's actually a lot of code to build the planner, and I don't want to get too into it here. Give it the logical plan and give it the desired output traits. So all we're saying is like, hey, Calcite, take this node and try to turn it into the white convention for me. And that's kind of all you have to do. And then the trick is like, okay, how do you write the rules and various things? And then how do you output it to substrate, which I'm going to talk about a bit as well. Let's focus on blue for now. So blue is a simple system I'm treating it as such that allows table scans and then very basic equality predicates. So only like equality between literals and field references. There's some scaffolding required to get blue working. So we have to model the capabilities of the blue system in Calcite in order to plan for it. So blue has a table scan node and a filter node. It's got 2 rules, blue filter rule and blue filter split rule. And it's got a substrate producer to make the substrate, right? In order to kind of enforce that, we only, or let's take a step back. I only want to convert filters to blue if they contain predicates that are purely executable in blue. So here is some simple code that kind of says, hey, given a filter, check that all the predicates in that filter are like is either a top level and or just a bunch of ands and equals. And hey, each of those predicates is an equality check, or it's equals of a call with 2 arguments, one of which is literal and one of which is a rex input ref. This isn't particularly interesting. You can combine this with the rule that you create for blue for the blue filter to be like, hey, I'm declaring a blue filter rule where I say, hey, I'm going for the logical filter. I'm going from the logical filter to the blue filter, so convention none to convention blue. And then you're saying, hey, when you match this rule, double check that the filter you're trying to convert to blue is a valid blue filter. And in the case that it is, you just make a blue filter. And that's kind of all you have to do to restrict the kind of filters that get converted to blue. The trick here is that might also remove the ability to push other filters. So if you have a condition that has a predicate that is blue compatible and one that isn't, then you need a rule to split those 2 things up. And that's kind of what the blue filter split rule is. You say, hey, give it a logical filter, split it into 2 components, one of which is executable on blue and one which isn't. And when you combine these 2 rules, you can do something like this to be like, hey, given a select the name of the customer where the nation key is 5 and the name is greater than G. Where this like C name greater than G can't be executed against blue, but it does work on white. So you go from this SQL plan to this logical plan, and then to this physical plan. And all you need for that is those two rules, and I guess maybe some of the stuff I'm about to talk about. So here's like 3 things we haven't talked about yet, like white project, white filter, and blue to white converter. White filter and white project aren't actually that interesting. If you look at how blue filter works, you have the blue filter node and a blue filter rule. You do the same for white project and white filter, and you have a white filter rule and a white project rule. That's not that interesting. Blue to white is a bit more interesting. So blue to white is a converter rule that, blue to white, the blue to white converter is a node that represents the movement of data from blue to white. So you just declare it as a converter rule, or as a converter implementation, and then you have an associated rule blue to white converter, which says, hey, at Calcite, any point in time, if you have a node in the blue convention and you need to go to the white convention, just insert a blue to white converter. And with like those 5 rules, that's kind of all you need to like plan that query roughly. There's not any optimization happening yet, but it's kind of all you need to split it into like the blue component and the white component, and then the boundary between them. And now we get to the point of like, okay, cool. So I've got this like Calcite subtree. I want to send it to some system, my executor, and it doesn't know about substrate, or it doesn't know about like this Calcite tree, right? And the trick is like, we want to figure out how to encode this subtree, this blue subtree, in a way that our executor can handle it. And let's say that white, in this case, is like data fusion. Data fusion actually can handle substrate pretty well. But we need to encode the leaf of it, the blue leaf, in a way that is compact for it. And we're just going to use a name scan. There's a little bit of utility code that I've elided at this point to be like, hey, I've marked all of the blue relations with this blue rel to put a visitor on them. Because it turns out when you're converting from trees to another tree, you kind of tend to visit them a lot. So what you can do is when you're visiting that blue to white converter, you say, oh, I'm at a blue to white converter. I know the subtree is in blue. I'm going to visit it. I'm going to find the table scan and just store that in my visitor. And then I'm going to add all the predicates into a list of predicates to have. So you kind of gather the information. And then you can, this slide is probably too small alive, so I won't get too into it. But effectively, you can visit the subtree and then say, cool, I have all the data I need to build a name scan. I have the table, which gives me the substrate schema. I have all the filters, which I can then convert to substrate filters using the machinery. And then I can build a name scan. And that's kind of how you can encode a blue subtree into a name scan. But what about if your like plans aren't really easily encodable into substrate, or if the system you're trying to target can't understand substrate at all? So let's imagine that red is just Postgres, right? So here's some of the scaffolding for it. We've got a red filter, a red join, red project. We've got a filter rule, a join rule, a project rule. If we were actually modeling Postgres, we'd also want like a red sort, red aggregate, and kind of all of the relations that you'd want. But this is sufficient to kind of model this query where it's like, hey, I'm just doing a join between like the supplier and part supplier. And the trick was that for blue, we figured out that our executor can look at that name scan on the blue table with that predicate, and it's probably smart enough to build the API call it needs to send to that system to get the data. But Postgres doesn't understand like substrate. Our executor could take this like subnode as a substrate tree and generate the SQL for it, but then we'd have to implement that. So why don't we just use the Calcite route the SQL converter instead, which is what we can do. So what we're going to do is we're going to collapse this subnode into a SQL query in Calcite and embed that into the substrate plan. The way you can do that is first by declaring a protobuf extension, because we saw that, hey, you can shove any messages into the system. Let's make one. So here we have a red query, which takes a SQL query and the schema of the output, right? We make an associated Java object, so the red query, which implements the leaf rel detail, which again has a toProto message or toProto method, which generates that red query message that we've added. And that's just kind of protobuf machinery. It's not that interesting. And then we can also just use the Calcite machinery, which again, isn't that interesting. You say, hey, I have this subtree that I want to convert to SQL. Cool. Make a new rel to SQL converter, make it the SQL dialect, or make it the Postgres dialect, sorry. Visit it, make the statement, and then embed it into the plan. And this one I will show you the output for, where if you look at the protobuf JSON for it, you end up with a message that's like, hey, there's an extension leaf of type red query, where the query is in the plan and it's got the schema. And as long as your consumer knows to look for the red query and knows how to handle it, it can be like, oh, I'm executing this plan. I get to a red query node. Oh, it's a SQL query. I don't need to know anything about it. I just send it to Postgres, right? And it just works TM. Now, for all of this, we've sort of been using Isthmus behind the scenes. So the conversion is happening in this color substrate producer, which extends the substrate rel visitor. This class in Isthmus knows how to go from Calcite to substrate. And what we have to do is we have to extend it and wire in our custom relations. So the red to white converter and the blue to white converter. But if you're just using standard substrate constructs or standard Calcite constructs, you don't even need to do this. You only have to do this if you're adding your own things. But that's kind of how you use Isthmus. You kind of just use the tooling and you add in any bits that you need for yourself. Now, green is TBD because it turns out I tried to shave a yak for this presentation. There's a lot of yak to shave. So for to-dos for what I want to get done in color is implement green, apply Calcite field trimming optimizations because they're quite powerful, configure join reordering, and then kind of demonstrate going from substrate to Calcite. And then just kind of had more examples. I kind of want to build up on this to show how you can use the system, use Calcite and use substrate to kind of make plans for federated systems. Some challenges working with this, with like substrate and Calcite in general, is mapping between substrate and Calcite functions can be quite tricky. There are functions in like the substrate spec that have slightly different nullability outputs than the Calcite versions, and that can be very subtle to debug. Calcite, technically the root of a plan is a rel root and not a rel node, and sometimes the distinction doesn't really matter, but it sometimes does, and we haven't quite got the right mapping there. And then in terms of the general challenge with working with Calcite, at least for me, has been that the best way to learn about Calcite has been reading the code, and sometimes it can be hard to find overarching examples to get stuff working. And I'm hoping that this will kind of help or be a bootstrap. That being said, that was a lot. If you have more questions, feel free to pop into the substrate community Slack. I am there pretty frequently, so if you ask questions there, we will find you. And then there's also a mailing list. And I see that there are questions in the Slack or the Zoom. That's what I'm looking for. I'll start with that one that I can ask the room.
So yes, the first question says, how does Calcite, substrate, and protobuf version evolve and maintain compatibility with one another? Are they not changing much?
I would say that the substrate core spec is changing a fair bit. We do make protobuf changes fairly frequently. The majority of them are backward compatible. We don't tend to make breaking changes a lot. However, we are pre 1.0, so we are moving quite quickly. So sometimes we do figure out that, hey, this is a bad idea, we need to fix it. How does the Calcite? But yeah, I would say that substrate is like actively evolving and it changes. It's improving week by week.
So there is another question by Julian.
Yeah, it's rather a long response, so, but because you did a great presentation, Victor, so let me try and, I don't know, deliver it in bits and pieces. I've been thinking about this kind of stuff a lot. In fact, I was originally scheduled to talk this evening about making Calcite's dialect tests work properly, because as you say, you rely on rel to SQL converter just working, and I think our tests for rel to SQL converter are completely inadequate, given that we claim to be able to translate any relational algebra to about 15 different dialects. And the test suite currently checks, we will like cast something as an integer and we'll try it on Postgres and try it on MySQL, and we won't even execute the SQL. So our our dialect testing is woefully inadequate. So it makes me think that we need to do some refactoring here, and maybe we need some new open source projects that are in Substrate or in Calcite or somewhere in between. And one thing I think we need is if we had a component which is currently rel to SQL converter that can take a piece of relational algebra and convert it to any dialect to SQL, if this thing existed, right, and it was well tested, then it would be a lovely thing. And you know, I can imagine Python-based projects would like to use this, right? So that's a place I'd really like to get to, and I'd like to, you know, talk to Substrate. A few months ago, I considered actually proposing a project called Substrate SQL that would just take a Substrate plan and convert it to any SQL dialect you wanted. And maybe just break off the rel to SQL converter and like donate it to Substrate Java or something to make it happen. The hardest part is the test suite. And what I'm working on is not just run the tests and check that the SQL looks good, but actually have a way of running it against Postgres and a way of running it against BigQuery to check that it actually works.
What I'm going to say to that actually is I actually kind of want to go further. Is like I actually don't want to generate Postgres SQL. I want to be able to give Postgres Substrate. I want to be able to give Trino Substrate. I want to be able to give every system Substrate. Like for me, going to SQL is a clutch because the system doesn't understand Substrate. And there's actually a lot of newer systems. I think Data Fusion and DuckDB both consume and produce Substrate. So you can just straight up give them Substrate plans. So in my ideal world, I would actually parse SQL once and then never look at SQL again. It's all Substrate all the way down. But in the world that we live in, a lot of systems do require SQL, and that's kind of why it's good to highlight in Calcite. It's like, hey, I don't want to have to do this. Calcite mostly does it for me, and I don't have to write one of these things.
You know, there used to be a language called Esperanto, which was a proposed global language. And if everyone just learned Esperanto, we would be fine and there would be no war. And these days we don't use Esperanto, we use Google Translate. And if I go to Thailand, I use Google Translate and it translates into Thai, right? So I am proposing Substrate is Esperanto. I propose that we have a way of converting to whatever the local SQL is, whatever language that engine happens to speak, which is going to be a dialect of SQL. If it speaks Substrate as well, that's great. But an awful lot of systems are going to speak their own little dialect of SQL. And let's just, yeah. If everyone was wise, they'd get rid of, yeah, SQL is Babel. SQL is many Babels, yeah. Okay, so that was one thing. I would love to create this project that can translate Calcite, algebra, and or Substrate into any given dialect of SQL and have a good enough testing framework that this stuff just works. And you know, I'd love to see 20 contributions a day coming into this thing, right? And so the hard part is organizing this project so we can accept all these contributions. The other thing is, I saw I totally agree the way you're organizing things, have a kind of red to blue dialect converter or a white to blue dialect converter, and you look at an expression like a substring function, you have to figure out, does this thing implement the substring function? I think there's a subcomponent here which is being able to say, let's suppose blue is Cassandra, right? Mm-hmm. I want to know, does Cassandra support substring? And if so, what does it call it substra, right? What's the local version of substring called in Cassandra? If that thing existed, then it'd be a lot easier to write the kind of code that you're doing. And we should refactor Calcite so it's much easier to just ask, can Cassandra support substring? And if so, what is its local variation of substring called? And yeah, we should do that work. Volunteers welcome. But anyway, I thank you for your talk. You've clearly done an amazing amount of detective work. So that's all I have.
Yeah, thanks so much.
So I think we have 1 minute for one last question. So I see that Anders Swanson asked, can you explain the business problem of the red, blue, white that you were talking about? Is it to enable single queries handled by more than one engine?
It's more that in systems that we work with at work and in other places, sometimes you have data that's split across various systems. And the naive approach is just like pull all the data into like your executor and then run it. But it turns out a lot of the time, if you can do like smart pushdown, you can like vastly reduce the amount of data you're operating on. Something I didn't touch upon in this talk, and to be honest, I still don't know how to do. I don't have a good idea how to do. Is like dynamic pushdown would be like really useful to be able to encode in like the planner somehow to be like, hey, run this subquery and push it into this subquery in this other system. Like there's a lot of, I guess, this is kind of one of those things where like the data is where it is and you're trying to gather it. And in an ideal world, maybe it would all be in one system or like you'd have a better cataloged. But in the world that you have a schema that you're given across these systems, you want to figure out what's the best way to run this and kind of what's the most effective and efficient way to run it. And red, like the red, green, and blue is kind of an abstraction of like, hey, sometimes you have systems split across data. How can you get Calcite to kind of be like, okay, push this down here, do the join here. And this isn't intended to map to any specific system, but it's kind of like a category of system where you're like running queries across different databases.
Great. So let's thank Victor for his great presentation. I learned a lot, but I don't want to wait much more time here. I'll catch up later. So
thanks, everyone.
And now let's move to the second presentation of the day by Mihai.
So this is the first time I'm giving this talk, so I feel it's a little long. I welcome you to ask questions at any time. I'd rather not finish it than you not understand what I'm talking about. And Calcite will not show explicitly, it's all implicit under the hood. It's at a very abstract level of semantics. Right, thank you. So I'll motivate this with the following example. So you have a view, which is a standing query. And it's a simple view. Let's say, aggregate data by month and by compute the average price for every month for each item. So if you think of this as a standing query that runs forever, it will have to build some state inside. It has to remember what it's seen so far. And this state will grow unbounded because you never know whether some item will show up for some month that you need to update. So if you know nothing about the order of the inputs, the state you need to keep here will grow without limits. And many systems can't cope with that. So can we do better? Well, we'll make a small assumption. We'll assume that the inputs are not too much out of order. So even when you file your taxes, the IRS says you have to file your taxes by April 15, and that's it. Otherwise you have to do something else. So that's a limit on how late the information comes to the IRS when they can compute what everybody owes. And we'll call that lateness. I'm not sure how to operate this clicker. All right. How do you go back? All right. So the solution we'll build will entail garbage collecting the state. So we want to automatically remove the state that will never affect any future outputs. If we can do this automatically, then we can pretend we run this system forever and we'll produce the exact same result as if we had the infinite state. So this is not a new problem. People who build streaming systems have done a lot of work about it. So what is new in what I'm telling you? Well, first of all, we're trying a principled solution. So I looked at some of these systems. I could never exactly understand what they're supposed to be doing, whereas I want here to be extremely precise. Second, we want to take this approach, this very cute paper, it's called One SQL to Rule Them All. Many people build streaming systems, and they are custom systems. They have weird operators, they have state manipulation primitives, and they slowly gravitate towards using SQL because they need to manipulate collections of events. And they want to re-implement everything that is in SQL, and they morph more and more towards SQL. But I think it's much wiser to start, designing a new programming language is very hard. You will get it wrong. It's much wiser to start with an existing programming language that people understand and that make it work to to solve your goals. And this paper proposes tiny annotations to SQL that will adapt it to the streaming world. And this is the approach we're taking here as well. And we want everything to be automatic. We don't want people to write state management at all because they will get it wrong. Okay, so the presentation has 3 parts. I will first describe incremental view maintenance as a streaming problem. So maintaining views and streams computations are the same thing, really. Second, I will talk about the data representation format we call Z-sets, which is very good when you deal with changes. So turns out database, they suck at dealing with changes. It's very, very difficult. But if you adopt such a representation, many things become much easier. And finally, I will explain how these two can be used together to do state garbage collection. All right, so the setup is this. We have a database. This is a database. You have a query which computes some table. And we are in the case where the database, the database keeps changing. So time goes from left to right. And as you update your database, you have new versions of the database. And we are in the realm where we actually, all these changes, people call them transactions, right? So these are boundaries when the changes become visible. And we are in the realm where we want to have a standing query. A standing query is defining SQL as a view. And what it means to have a view, it means that every time your database changes, your view should reflect what's in the database at that moment. So you can achieve this by essentially running this query again and again every time the database changes. And if you do that, it will work, but it might be expensive if the database is large. But what we want to do, we have to think of the problem this way. Instead of computing each view again, how about we compute the changes to the view? Maybe these are much smaller. The yellow arrows are much smaller than the blue arrows, than the green arrows. And so how about if you're given a query Q, which is green, we can somehow create a blue query called Q delta, which is applied not to the database, but to the changes, because these changes are very small compared to the database itself. And hopefully these changes are also small compared to the view. Maybe this query can run much faster. Ideally, we want the work that we do is proportional to the size of the change and not to the size of the database. And this is what incremental view maintenance is about. And it turns out there is an automatic, and it's actually a trivial algorithm to convert an arbitrary query to its corresponding Q delta. But that's not what I'm going to talk about too much today. We'll assume that that algorithm exists. I mentioned it in a previous Calcite meeting. But yes, query.
So the operations on delta to compute the delta on the view would only work if it is sum or something like that. But you have to make an assumption about the kind of operations.
So you're asking me, do I restrict the queries that can I transform into incremental queries? No,
right.
I'm not.
Okay.
So anything you can write in SQL, you should be able to do Q delta for. It might not be always very efficient, but you can do it. Yeah. So that is doable. And we can talk about it if you want later. And I have another presentation about that, but it's not this one. Yeah. Okay, but one question which is very important is how do you even represent these objects, right? So if you look at this, sorry, we have these two deltas. So we want to compute on deltas. These deltas actually can be negative because you can delete rows, and you can delete rows from a view, right? When you aggregate, for example, the old aggregate disappears and the new one shows up. So these deltas are different objects than most databases deal with. Most databases think about tables and adding rows to a table. When they execute a query plan, they have an iterator which keeps adding rows to the result. But they have a very big difficulties dealing with negative changes. But it turns out that that's not necessary. So you can, there's a very simple format. To every row, you add a weight. The weight is an integer. The integer can be positive or negative. And it tells you whether, how many times the row belongs in a specific table. So this row is here twice, SQL works with multi-sets. So you can represent multi-sets, but you can also represent deletions. So it says this row will be deleted from a table. And this also looks like a table. So it's some object that the database understands. You can model it as having an additional column to the table. Turns out that you can implement all of the relational algebra using Z sets. These are, Z comes from, the integers. And actually, Z sets are everywhere. What am I doing wrong? Yeah, now it seems to work.
I think just a connection of lags.
Okay, so it turns out that you can use Z sets for many things. You can use Z sets to represent both the tables and the views. You just have positive weights. But you can use the Z sets to represent the changes to the tables and the views, arbitrary changes, not schema changes, just data changes. But you can, what are change data capture streams? They are nothing but Z sets that describes how your database is changing. A large part of database logs, at least the ones that describe changes to the data, not to the schema, can also be encoded as Z sets. And insert delete statements can be encoded as Z sets. And the transactions can be encoded as Z sets. So transaction is just a set of Z sets applied to different tables. And I claim that Z sets should be a standard data exchange format. And I have a slide about Z sets and data lakes, but I took it out because I don't have time to talk about it. But if you do work on data lakes, let's talk about it, because I think Z sets can solve a lot of interesting problems for data lakes as well. Okay, and Z sets are great because they can encode tables and changes. It turns out everything you do on database you can do on changes, right? So if you have select, project, join, those work just fine on Z sets. There's no problem. They just carry around the weights and do some arithmetic with the weights. So this is a query plan. These arrows will be carrying Z sets and not just sets, or multi-sets as in traditional databases. Okay, and turns out actually you can extend this to carry not just Z sets, but streams of Z sets. Remember, the database keeps changing. You keep adding, making changes to it. So by using double arrows in these plans, I'm just showing the fact that these operators will now process a stream of changes. And that database, when they run a plan, actually, they do work in this way because they have this iterator model that iterates over the elements that will be produced in the result, in the inputs and in the outputs. So they do operate already in streams. So streams are not foreign to database engines. The Z sets are a little foreign. Okay, so whenever you see a double arrow, it means we are computing on streams. Okay, so there's actually a very cute stream operator, which databases don't usually make explicit, is the delay operator. Given a stream, it will give you the same stream, but a little later. So when you feed it an input, it gives you the previous input as output. And it starts with a 0. Think of the 0 as the empty set. Well, it turns out that this is the only operator that you need to manage. This operator stores state because it has to remember the previous input, and this is the only operator that stores state. So you can build all of a streaming engine with just this operator to manipulate state. And the trick is to use this integrator. So we put together two operators, a plus, think of it as set union, and a delay. And what this does is just takes the current output and adds the current input. So this is, O is O plus I. So this is an integrator because it receives, think of this as a stream of changes. It accumulates all the changes, and the output is whatever is in the table at this moment. So this is an operator that converts a stream of changes to something that tables. And say, oh man, I came here to the meetup. I always hated calculus in school. Why do I have to learn about integrators and all this bullshit? But I claim integrators are not that strange because you are an integrator, right? So look at you, what are you doing? You're sitting there listening to me. My words come to you as a stream. There's a stream of experiences that you're being affected by. And what happens in your brain? Well, in your brain, okay. In your brain, you integrate these experiences. You accumulate the information I sent you, and you build a mental picture of what I'm trying to describe there. So integrators are not some bizarre mathematical object. We are all integrators. We are all streaming systems. And databases are just a particular case. They are also integrators. They integrate the changes, accumulate them as tables. Okay, so don't be afraid of integrators. But, you know, it would be great if this was the model, but actually it's not healthy to remember everything. So it turns out that you can make an integrator. I forget a lot. So you can make integrators forgetful too. And it's very simple. The way you do it, you took the integrator that you just had before that would remember everything it's seen. You just put a filter here. And this filter will actually tell you, you know, whatever is not accepted by this filter will be forgotten. So I've built now a very simple circuit that can remember things, but also can forget them. And this is going to be the idea to do garbage collection. If we tell this filter what to forget, that state will be lost. The state will be kept in integrators in our circuits, and then we can selectively choose what to forget. Great. All right, so now let me show you. So let's do an example. So we want to implement this simple query, distinct query. So we have a stream of changes. Remember, we are in the streaming model. We get changes to the database. I insert a row, I delete a row. You can delete many rows, insert many rows. This is what we have there as input. What we have to produce as output is what are the new rows in the distinct. Okay, so when I insert a row in the data table, what is the output? Well, how do we compute this? Well, turns out you can build a circuit for it, and the circuit looks like this. The circuit actually has an integrator. Turns out that when you get a new row, in order to know whether you have an output or not, you have to know whether you've seen it before. If you've seen it before, the output will be empty because it's not a new row, so it's not in the distinct. If you haven't seen it before, then you have to emit it to the output as well. All right? So this is what this integrator does. This actually reconstitutes the data table itself. Here we have the data table at each moment. It's a series of snapshots of the table, reconstituted for the changes. Then here we have a delay, and this gives us the previous version of the table. The table, we had a previous step, and we look at the current input, and now this operator looks to see for each row in this change whether it was in the previous table or not. And if it wasn't, it's emitted as the output, otherwise it's not emitted as an output. And this works for negative changes too. When you delete something, if it was in the table, then the way it was goes from positive to negative, it means it's no longer in the table, then you emit it as a negative change to the output. So this is a circuit that implements the incremental version of distinct. And we can do the incremental version of any operator that you can write in SQL using similar tricks. But notice that this integrator accumulates state. It has to have the whole table, and the table could become very large. All right. So in general, this is a point I want to make. The streaming system, so even if you start with a query, which is a stateless query, in the sense that you can run it over the database and doesn't remember anything, when you build the incremental version of a query, the incremental version of any query, it will have state inside. The state will be kept in those integrators, the same way you keep the memories in your head. And this state, this is what we want to bound now. This state, don't want it to become too large. Okay, so now, as I said, you can't do this in general. If you don't know anything about the order of arrival of inputs, in general, you might need to keep all the state. But how about we add a little annotation? And the annotation says, you know, this is a timestamp, and I'm saying it can't be too late. So this is here an integer, but it could be any data type which has a subtraction operation. So let's say this is the time, and this is the value of this TS integer, right? And you know, these are the TS integers that show up in the data. And now from each of them, I will subtract 5. So these distances, the red dots are all 5 less than the data I've received. And now what we'll do, we'll build a line which shows us which is the largest red dot we've seen so far. And we call this the waterline. Okay? So this says, you know, I promise you things will not come too much out of order. And this means that every time a blue dot is above the gray line, the promise was kept. There is one guy here, and this guy was late. It wasn't supposed to show up. So it's like, you know, filing to the IRS in May. Yes?
Is the waterline the same as the watermark concept in the one SQL to rule them all paper?
Yeah, so that's a very good question. I never found a formal definition of watermark, and many people use watermark with overloaded meanings. So it seems similar to watermark, but exactly because I didn't want it to add one more meaning to this notion, we called it waterline.
Okay, I need to introduce you to Tyler Akadau, who originated the concept. He was a co-author on the OneSQL paper, and you guys should figure out whether it's the same concept or a different one.
Well, I suspect actually it's intended to be the same concept, but I couldn't find a definition. But here I'll give you a definition by giving you a circuit that computes the waterline for an arbitrary data source. So this is the change that comes to your data. We project on the column that has a lateness. Actually, by the way, you can have any number of columns, and each of them can have an independent lateness, and they are computed in parallel. So there's no restriction. There's no special timestamp notion. Then what we do, in this change, it has many rows. For all the rows, we aggregate and take the max. That will be the waterline. And then we subtract the lateness that was given. That really gives you, so first of all, we do this for batches, right? For each transaction, we do it. It's not a row by row, but transaction by transaction. And for each of them, we take the red to be the max minus the lateness. And then we have this max operator. This is an aggregate max. This is a binary max, which looks like an integrator. It takes the previous waterline and the current waterline and outputs the max. So this is semantics. So this is 100% mathematical precise definition of what waterline is. So there's no ambiguity. Now we can call it watermark if you want. I have no problem with that. And if that's the intended definition of watermark, I think we should all agree on that. But the point is, this is how you compute the waterline of a data source, which has the specified lateness. Okay, so waterline, the idea is you should think of a lake, a reservoir where the water only goes up. And the waterline is, the water goes up and down, but in general, it will go up. They talk about global warming and will be all flooded. So I think this is a very accurate depiction of what happens. The question is, what's the lateness? Anyway, so I'll skip over this because let me show you something else which is interesting. So this is the waterline for the input, but how about when we compute on data? Let's say you have a computation, we take the timestamp and do some arithmetic on it. Well, it turns out that if this computation is a monotone function, so this is a monotone function of TS, then the output also has a waterline. And you can compute the waterline using an operator that essentially depends on what this computation does. Remember, the waterline is not a collection, it's just a scalar. So you project on the column that has a waterline and you apply a function that looks like the function that you select, and you get the waterline of this output. So you can carry waterlines through query plans, essentially. But this only works if this function is monotone. And this only works if the arithmetic doesn't have wraparound, which is why I spent some time in Calcite to make sure that you can specify arithmetic which on overflow will actually crash rather than wrap around. Because if you add a positive number and it becomes negative, then it's no longer monotone, so your waterlines are screwed. So this is very nice because waterlines compose. So let's say you have a query plan, and a random query plan, then what you can build is you can build a parallel plan to the query plan, which computes the waterlines. For each of these operators, you have another operator, a yellow one, which computes the corresponding waterline. These are changes, and these are singletons, because the waterline is one scalar value, it's not a collection. Okay, so now we'll use this fact. This is the incremental distinct I've shown you. Let's GC it using the waterline information. Why can you GC? Why can you forget about state when you do distinct? Let's say the distinct has a timestamp. If the timestamp only goes up and it never goes back to much, let's say the latest is a month. After you have seen something a month in the future, you'll never change the items that are more than a month behind. That's the intuition, right? So this is, remember, we had an integrator, which I made much bigger, and a delay in this operator, which used to check if something was previously there. So first of all, we compute the waterline, and the waterline of distinct is trivial. It's actually the waterline of the input. And then here is we replace the integrator with the forgetful integrator, the FI. And then we use the waterline to feed the filter. The filter says anything that is below the waterline you can forget because it will never change. And this is the query plan of a query which computes distinct, running forever and using only as much memory as needed. Everything that is too much in the past is guaranteed never to change, so it's thrown away. Okay, so this is exactly a perfectly mathematical description of how this should work. This is called the controlled filter, because it's a filter which is controlled by this value that comes from the side. And you do this actually with arbitrary query plans. You have a query plan which has integrators. Joins actually turn out to have integrators. You actually drive them by from the corresponding waterline. And joins are very funny because the right side of the join garbage collects the left side of the join. But that's something I don't have too much time to go into. But this is how your query plans will look. They have, this is the data path, which is what any query execution engine has. And this is, you could think of as a little control path, which handles the GC. You could think of it, you know, query engines do already have, like, to maintain statistics, they have side computations that don't handle the data in the tables. This is just another kind of side computation that is parallel to your plan. And it turns out we can do many operators under some conditions. I'm not going to go through this slide. You can do select where, distinct, join, as of join, tumble, hop, window aggregates, lag lead, assuming that some of your inputs have waterlines. If some of your inputs have waterlines, then your outputs will also have waterlines. This doesn't mean you can do any query. For many queries, you know, if you don't compute nicely, you don't do monotone computations, we will lose the waterline. But at least, you know, we have a recipe, and if you give me a query, I'll tell you whether the output has a waterline. Okay, so I told you a lot. So let me make a little summary of what I've told you. First of all, you should think of incremental computations are computations that compute directly on changes. Databases don't compute on changes, they compute on tables, but incremental view maintenance is all about computing on changes. And changes are actually not a foreign object. You can use this simple table format called z-sets to represent both tables and changes to the tables. And they add up very nicely. They have a beautiful algebra. So they can be mixed and matched in arbitrary ways. In general, incremental computations are stateful. If you write a query, which you can think as a, you know, SQL is actually a cute language from this point of view. It's a pure functional language. It has a very unspecified semantics, but if you choose a semantics, it's actually a pure functional language. Well, these incremental computations are not like that anymore. They are stateful computations. They have internal state, which they need to mutate. But the beauty is that their semantics is defined by the SQL. So this is why we want this one SQL to rule them all, because it tells us exactly what the incremental computations that have state should compute. And in some of these, the state might grow unbounded, and sometimes there's nothing you can do. But sometimes you can do something because you can show that some state will be irrelevant for future outputs. And then, you know, integrators are everywhere. You are an integrator. So if you remember nothing from my talk, remember this picture. So that's how we all process information. We integrate the data that comes to us. We are very much unlike all these AI systems that in parallel train all the weights. They also, you know, kind of stream through the inputs, but they are much more parallel. But that's a digression. Okay, so lateness is an annotation that promises that the inputs are not too much out of order. And I've seen similar concepts. Some people call this watermark, by the way. So I never understood exactly. So we define it as lateness, and we have a very precise semantics for it. And the waterlines tell you essentially which data will never change. That's what a waterline is. So you can compute a waterline for each sub-query of your query and carry that forward. And, you know, forgetting things is a very healthy behavior. Otherwise, all the people that upset me in my life, I would probably have a grudge against them. So, and it's very good for garbage collection too. State may be garbage collected by having these forgetful integrators in your query plans. Okay, I'm sorry if it was too fast. Take questions, or I can tell you about data lakes and z-sets.
So are the questions here in the audience?
So just going back to the watermark versus waterline, the intention of watermark is a general concept that can be supplied by the system. So it could be defined based on lateness. It could be based on a wall clock time. It could be based on some punctuation events that are sent through the system. Like the source system says, I guarantee we've seen all data up to 5 p.m. So a watermark is a generalization of it is a constraint on the time that only increases, but can be supplied by the system and can propagate through the query. So you've got you're using a common variation of this, which is based on lateness, but we wanted to allow other forms of watermark, other ways of saying the data is too late and therefore can be ignored.
Actually, that's a very important point you've made there, which is the fact that water lines are always carried by data. So if you have no data, the water line will never advance.
Right.
So it cannot express what you said is look at the wall clock time, which is a completely different data source, and based on that advance the water line. Yeah.
Yeah, and there's this concept called punctuation, which is not data, but it's simply like if you want to, for example, you're doing a stock trading system, you want to say, I've seen all the data for the day. You want to inject something in the system says 5 o'clock has happened, there are no more trades of the day. You want to be able to inject that without actually sending some data. So I don't know whether this is an addition to Z-sets, a way of adding kind of rows data that can be carried along with the Z-sets that represent the absence of data, but aren't actually considered data themselves.
Yeah, you can do it this way, or the now function is actually a function which essentially injects rows into a fictitious table of a clock table where rows only advance and have zero lateness. So if you can join against the table, you can actually get this effect too. Yeah.
Yeah, maybe you can talk offline, but I'm trying to get an intuition. Let's say you do a min. Okay, if you get a new min, but you forgot the lot of the history, but you don't know the new min is there is something in the forgotten history which is minimum than the new min. So because the min is not a associative function. So
you're asking how you do minimum incrementally?
Yeah.
Is that the question?
Yeah.
Yeah, so the minimum is very much like distinct, essentially. So remember, distinct keeps all the data around.
Mm-hmm.
And when it gets in some new data, checks to see if it's seen it before.
So you will check the entire table though.
Well, so for min, if you do a min or something related to the timestamp, so first of all, if the data has lateness, you know that some rows will never be deleted once they become very old. You're guaranteed that they will stay there. So the min will be always bigger than that. So you can still do a bounded memory min.
So maybe, okay, I'll do.
Min is difficult, but there are versions that
There are versions. Okay.
Are there any other questions for Mihai? Are there questions in the chat?
So this all exists. It's not just ideas. So you can actually play with the system, which has all this built in.
I have a last question. So since this is a real system, and since you mentioned that you are working with Calcite, so all these Z-sets and the integrators, have you extended certain parts of Calcite in order to implement this, or it was all the primitives were there and...
It's funny because last time I gave us a talk in this community, Julian said that there is an integrator in Calcite, although I don't know where it is. Okay, so what we do is actually we use Calcite for planning, and the plan turns out is agnostic to the fact that it cooperates on changes. And then we lower it into a representation where we have you don't even need an integrator. The delay is the only thing you need, but we do have an integrator operator because it's handy. But it could be done in Calcite. There's no reason it couldn't be done in Calcite. it's that I wasn't, when I started this, I wasn't as familiar with Calcite. I'm not as familiar even now. It's a big project. So that's the main reason I haven't done it in Calcite. But this all could be done in Calcite. There's nothing fundamental here.
Okay, thanks a lot. Thanks, Miguel. Okay, so the next presentation is by Wala. So I'll pass the mic to him.
Thanks, Stamatis. Do you hear me well? All right, so today I'm going to talk about Coral, which is a SQL Interoperability Engine, and talk about some of its use cases in multi-dialect support, incremental maintenance, and data compliance. So recently we've observed that composable data architectures are becoming mainstream in data lakes. Especially at the storage layer, there has been a lot of standardizations across concepts like table formats and file formats. So for example, we've seen compute engines interoperate between tables and views, where both are named entities, both return records to the engine and to the user so that they can process them in the query pipeline. Tables themselves are also interoperable between multiple table formats. We've seen long timer table formats such as Hive that stood the test of time for maybe 10 years plus. And then more recently, more modern table formats that address some of the gaps that were observed with Hive tables, including table formats such as Delta, Iceberg, Hoodie. And even those table formats are interoperable with file formats, where any table format can use any file format such as Avro, ORC, or Parquet. But more recently, this trend is not stopping only at the storage layer, but also it is growing to the compute layer as well. So there are new domains where we recently see query execution engines are becoming more pluggable or interoperable with multiple query languages, or can understand or interoperate with query rewrite rules that can be written in one format and then applied to multiple engines, or a query execution engine which can be implemented through multiple view catalog implementations. And to address the challenges of modern data lakes, specifically on the compute abstractions, we need a way to unify SQL interoperability across different engines. And here we position Coral as the solution for this domain of problems. So essentially, Coral provides a way to capture a common representation or express a common representation that can capture different SQL dialects or different view definitions, or different engine plan representations, or mechanisms to push SQL down between engines, or apply common query transformations and then have them interoperate between engines. But also, most importantly, ways and adapters to convert from input representations to Coral representation, or from Coral representation to an output representation. So as you can see here, the basic idea is to have like source dialects, maybe coming from source engines, such as Hive, Spark, Trino, or any future dialect. It can be SQL or some other relational language. There are like domain-specific relational language as well, such as like graph query languages or logical query language, and so on. In fact, recently, SQL adopted a standard for property graphs that is called PGQ. So that's a potential dialect that can be plugged into this framework as well. And on the other side, that input dialect can be converted to an output dialect, again, across the same dimension of those options. So as you can expect, Coral is based on Apache Calcite, and it has two semantically equivalent representations, which we call them Coral IR on the AST level. And this basically corresponds to Calcite SQL node representation. and it captures the query semantics at the syntax tree layer. And its typical use case is in language translation between dialects or between languages. And the other type of IR is the logical plan, and it captures the query semantics at the logical plan layer, and it corresponds to Calcite's rel node representation. And typical use cases for that representation are query optimization, query rewrites, and dynamic data masking. And we're going to see a bit of both throughout the presentation. So just to quickly jump into an example, this is Coral IR at the AST layer. Here we see the input as a Spark SQL query, and highlighted in red some interesting operators in Spark for the sake of that example. So we see the array access operator and the in-string function. That query is expressed in Spark SQL. Then, as we can see, we can convert it to Coral SQL node representation at the AST level. And that's a visualization of that representation. You can see, like, mostly it is expressed of tokens that are part of that query. And then on the flip side, it can be converted back to another dialect, which is Trino SQL. See throughout that conversion how some operators got converted to become like semantically equivalent to the source operator in Spark, but applicable for Trino in this case. For example, the array access operator in Spark SQL got converted to the element add function in Trino. Also, the 0 index of the array got converted to 1 because Trino array indexes start from 1. And the in-string function got converted to the string position function because that's the semantically equivalent function in Trino to that function in Spark. Similarly, this would be the equivalent representation of the same query, but at the other abstraction, which is the logical plan. And here we can see it like makes more sense to us in terms of like a computational tree. We have the scan nodes, then the join nodes, then the filter nodes, then the project node. Like a lot of the token stuff has disappeared now, and now we're talking like logical plans. Same idea applies. You can go from Spark to logical plan back to Trino SQL. As per the translations themselves or the expressivity of the type of conversions, like what was shown is basically just examples, but there are quite some sophisticated types of conversions that are implemented in the Coral adapters, including like how to do lateral view joins, user-defined table functions, window functions, and common table expressions. So what is Coral IR about, and why we think it's like a good use for all the use cases that we've mentioned at the query interoperability slide? So number one, it's battle tested. So it runs daily on hundreds of thousands of transformation in production jobs in LinkedIn and outside. It's also expressive because it captures a rich set of operators that we can convert between like two big engines such as Spark and Trino. And both boil down to Coral IR in the middle, extending a standard set of operators to support like multi-dialect as well. It's also multifunctional because it has two IRs, the AST and the logical plan representations. It's bijective because we can go from the AST representation to the logical plan representation, and we can go back from the logical plan representation to the AST, guaranteeing that you get the same query semantics. So in some cases, we've observed like in some of that, like out of the box transformations, this cannot be guaranteed. But in Coral, we have made sure that this transformation is truly bijective. It's also translatable because you can go from language to AST to another language, or from language to AST to plan to AST back to language. So either route of translation you can follow. And it's also rewritable because you can rewrite the AST or rewrite the plan, and then again end up in an ST or end up in a plan. And then you can compose those transformations at the second row together to build like a big pipeline of transformations. So some of the notable integrations of Coral are in Trino open source, where it is used to execute Hive views on the Trino engine. And internally at LinkedIn, we've integrated also with Spark, again, for the same use case in Spark, where views expressed in other dialects can be executed in Spark. So how do we go about the Spark integration? Basically through an extension to the Spark engine to make view interfaces pluggable. That was some recent work where we collaborated with the community to extend Spark to understand like view catalog APIs and view APIs. And then any translation can happen under those APIs as an implementation detail. So some of the future directions along the lines of inter-dialect transformations would maybe benefit from those use cases. So for example, we know that engines have to interoperate with table formats, and table formats have their own functions as well. It's not only that engines have functions, but also table formats for the sake of partitioning data, for example. So one use case is to have Coral as the way to interoperate between the functions at the table format level and the same function or the semantically equivalent function at the engine level. There's an example of such issue in the Trino project to integrate with Coral to resolve functions from Delta table format when dealing with Delta tables in Trino. Because Delta table format typically uses Spark functions, but Trino has Trino functions. Same line of thought can apply when pushing SQL down between engines. So a front-end engine can push a SQL expression down to a back-end engine. So that was the first use case along the lines of multi-dialect support. And the second use case would be along the line of incremental view maintenance. So I guess Mihai might have answered this question already, but I'm going to reiterate. Why incremental maintenance is because incremental maintenance allows us to process the query only on the changes and not on the entire table repeatedly, which leads to lower compute cost and also lower latency because you can make your compute much more frequent in this case and get insights much more faster. And also improved user experience because the user can think about the query in terms of the batch semantics, but then the engine or the platform can take care of the incremental way of computing the query. So this is incremental 101 in the case of joins. So here, let's start with evaluating this join query on a key between two tables. In the non-incremental way, let's say that we have these two data sets with this state at the beginning, then their join would be computed on the entire tables in T1. Again, if it's non-incremental, then there's new data. But in T2, we would have to, again, compute the join on the entire two tables and then produce the join results. But there was data that was already in the table that participated in the query in the second time. So that was kind of a waste here. So in the incremental case, what we would like to do instead is, if there is new data that's represented by the green colors in these two tables, then it's more efficient to join the green part from the right table with the gray part from the left table. And the green part from the left table with the gray part from the right table. And the green parts from both tables. And these three separate joins would constitute like the units of the incremental join. And the final query would be a union of all these joins where we can insert them to the previous result of the join from the previous iteration. And this way we can incrementally maintain the table. So how can we achieve that with Coral? So the idea is essentially, again, putting a pipeline of those transformations that I described in the pipeline slide, where the input is a non-incremental SQL and the output is an incremental SQL. So the input would look like this and the output would look like the select query, but broken down into three parts. And each part leverages like a delta input as opposed to the full table. So the pipeline basically converts the SQL to rel plan. Then the rel plan gets converted to another rel plan that has like three parts replacing the big join. And then the new rel plan is converted back to SQL. Yeah. Future work. Okay, we'll talk. So we've integrated this with DBT. You can see the integration code also on the Coral repo if you're interested. And this is implemented as a drop-in replacement to the materialization mode of table. But in this case, the materialization mode is incremental maintenance. So you just specify that in DBT and then write your query. Then you get the incremental execution for you in the background. Behind the scenes, there's also like some Iceberg and some Spark code generation that's taking place to achieve the full pipeline, because the query rewrite itself doesn't pull off the entire pipeline. So behind the scenes, there would be Iceberg snapshots that are generated or like an incremental scan for Iceberg tables that is generated to capture the last green part of each input table. And then temporary views would be created on that are then used in the Coral query in the first line here. And then the result of that evaluation, which would be stored in a data frame, you can then write this data frame or append it to an output table. So if you trigger this execution on like a regular cadence, then you get your table continually updated with the incremental results. So next steps, first expand this to more operators, including aggregations and outer joins, support updates and deletes, and build a cost-based model to identify optimal incremental plans. So in fact, like incremental doesn't have to always be better than batch. It could be the cases when the increments are large, then maybe we could do batch, which is a better option. Even within incremental, there are many ways to do incremental. So there might be, let's say a table has multiple inputs and each of them has incremental or deltas as input to them. We can selectively choose which tables to leverage the delta from and which tables to compute from scratch. So this kind of big plan space needs to be explored, and then a cost model needs to be devised to select the most efficient plan. And there's actually work in progress in that space where you can see 2 PRs here that are in progress. You can reference them to get an idea about like how this is done in terms of both the plan space generation and the cost estimation. So these are some references for some of the modules that I talked about throughout this part. Finally, the last use case is in dynamic data masking, and this use case has been like more important recently with all regulations around like GDPR and DMA and all like attention to respecting user privacy and like trade ethics. So the idea here is that data shouldn't be just delivered to the query as it is. There might be filters or some subset of data should be like pruned before getting returned. But most of the time it can depend on the context where like the query is being evaluated. So depending on the context, the type of data that's filtered might be different. And even it can depend on the individual rows or individual user preferences. So if you're dealing with a members data set, some members might have consented to something and some members might have not given the consent. So the space of permutations of like how to filter the data is pretty huge. So applying the filters at read time is pretty important in this case. And by capturing the environment where the query is running, as well as the individual user preferences, we can come up with the query on the fly that's a rewritten version of the actual query on the base data set. So as an example, this is just very simple column level masking example where instead of selecting start from user, then based on the configuration of the environment and which obfuscation function is required to be applied, in this case, we can add the obfuscation function to the name column. In this case, the entire name column would return, let's say, a hash value instead of the actual name. A more involved use case could respect also the individual preferences. So instead of the input query, which is select star from users, we can respect individual consents. And in this case, we have another table that stores those consents. And then we could rewrite the source query to become like another query that evaluates on a per user basis whether the hash function should be applied or not. And in this case, the output table would look like that, where some rows would selectively be obfuscated. With that, that's it for this presentation, and we can open it up for questions. It's actually a view. The implementation detail is a view. Yeah. But again, it could be a view or on-the-fly query rewrite. One concern with views is that the number of views could grow also exponentially given the number of use cases and which columns need to have the functions applied to. So there is a limit to how far you can go with views.
Thanks for the talk. Regarding the incremental view maintenance, costing, whether to use incremental maintenance or fully computing, are you aware of the Tempora project, which is a paper and also a contribution to Calcite that sadly I didn't ever finish integrating, but I think there's some really good work there that you could build on, or at least should be aware of?
I'm very aware of that work. I'm actually, at some point I was in touch with the authors and we heavily collaborated on that cost function, but the code was quite maybe hard to integrate with Coral. So let's put it this way.
Yeah, I agree.
So I think that might be the reason also how it didn't make it to Calcite.
Yeah. But anyway, it was. I think they were out of Alibaba, so they were dealing with some, real world. It was, proven on real world data, and so, whatever the problems they solved are probably problems you guys should solve as well.
Exactly. So it definitely inspired the problem statement here. We kind of implemented a simplified version of their paper. We didn't really require all the use cases in that paper as well. That was another reason why we didn't go full in on that, because their search space was quite huge for things that are beyond incremental maintenance as well. They have another use case that is called incremental data warehouse. That is not the case for incremental maintenance. It's like more generic use case. And that was kind of overkill just for incremental maintenance.
I have another question, but I'll ask it later.
No, thanks for the talk. So I see that you are translating from a set of well-known languages to other. Let's say if my company has our own dialect of SQL, but then under the cover I want to transform to any of these standard. Can I use this, or looks like it is not possible straight out? I need to do something, right?
You cannot use it out of the box. So you need to build the adapter for your language.
And is that something people have done with Coral?
Yeah. So like not outside LinkedIn, but inside LinkedIn, we have built a couple of adapters.
Okay. Is that something? Okay. Maybe I'll talk to you offline.
Yeah. The other data point here is if your backend engine is already like one of the implemented adapters, let's say Spark or Trino, then you get this half of the translation for free. You only need to build the adapter from Coral, from your DSL to Coral. And then the rest gets out of the box for free. Because that intermediate layer guarantees that it has very well-defined contracts. And if you stick to them on the input side, it's guaranteed the output side would be what you expect. Okay.
Are there any other questions?
So if I understand correctly, Coral is a set of intermediate representations that use the Calcite interfaces.
Correct. We use Calcite interfaces, but not necessarily Calcite's standard operators. So we've added on those as well.
So can you elaborate on that? Why did you need to extend and what is different?
Yeah. So we needed to extend because we wanted operators that would be translation friendly. and operators that would be able to capture the semantics of like two big engines, such as Spark and Trino. That IR is mostly stable, but I expect it to evolve as well when adding like more source and destination dialects. We might find that there might be operators that we still need to add, but so far we've added maybe 30 to 40 operators in addition to what's already in Calcite.
This is all Apache.
Coral is not Apache. Yeah. BSD.
BSD, okay.
So do you have any other questions for Walla? Yeah.
There's one more data point also regarding the extensions beyond Calcite. So this guarantee of going from from SQL nodes to Rail nodes and back to Rail nodes and maintaining the semantics, we had to extend Calcite as well to ensure that kind of isomorphism between the two sides. Out of the box, sometimes it doesn't work.
Okay.
We can talk about this, yeah.
Can you onboard this on existing data, or do you have to rewrite your existing data?
This has nothing to do with the data. So this is on the query planning path.
So in one of your translations, you added the delta ID. So where is that stored? I thought that was stored on the table itself.
Yeah. So that comes from, we add a Spark wrapper, Spark Scala wrapper around the SQL. And the Spark Scala would get the snapshot only of the delta from the source table into a data frame. And then you can register this data frame as a temporary view. This is how you get the underscore delta version of the table.
I was referring to the one where you do joins, the incremental join. So where are the delta IDs stored?
These are basically iceberg snapshots or any increment, like table format that supports incremental scans. You can get the deltas from that table format.
Okay, so if you're
like stored on disk, you can ask the table format to return a subset of the rows since you have last seen.
So if your data is stored in pure SQL format and no data lake format, we cannot use any incremental joins or anything.
Again, it depends on your database engine. As long as your database engine supports incremental scans, then you should be able to use that.
Okay, thanks.
Like CDC kind of framework. Yeah.
These sets would solve. If database will publish these sets, they will solve the problem.
Thanks. So I guess an observation and a question. The observation is what Relative SQL Converter is doing in Calcite, what you're doing with SQL to SQL dialect translation, and then what the first talk Victor is doing with Substrate. It seems like we're all trying to solve the same problem, and we've all developed independent solutions to the problem, and we're not sharing our work. So that's a shame. And it's a dilemma for anyone in this room who wants to solve the problem, because now they have to choose between three things, each of which are, incomplete. My question is, the problem I perceive is if someone is building this dialect to dialect system, the test framework is going to have to be huge. And to run these tests, you need to run lots of queries against Spark, lots of queries against Trino every night for every change, right? And these systems are flaky. You're going to get a lot of false negatives. So my question is, how long does your test suite take to run, and how do you manage to ensure kind of good engineering progress? In order while you're testing this huge set of dialect to dialect combinations?
That's an amazing question. Thank you for asking this. So right now, this runs for integration tests on the set of views that are internally defined at LinkedIn. And these are production views with varying levels of complexity. But exactly as you mentioned, they have to touch the production HMS. And there might be user errors in them. There might be tables in them that might have been dropped, so the SQL itself is not reproducible. And it helps, but I think it's a process that can be improved. And in terms of like how long it takes, let's say for 4,000 views, it takes about 5 hours to execute across all dialects and all possible permutations and produce results. That being said, we've realized this problem as well, and we're in the process of building like a benchmarking framework to do this on like a reproducible basis using a golden set of queries that are getting executed on the actual engines with deterministic data. That effort is not like open source yet.
All right. Well, I would love to share resources on this, and I think it's beneficial to carve off the problem of the scalar functions, so things like str, pos, and instra, and so forth, and the type system. I think it makes sense to carve off that problem of kind of just translating between the kind of function sets of the various SQL engines and dealing with the relational operations as a different problem. So I think it's useful to have a library and a test suite that deals with just dealing with the different SQL function sets. Yeah, if you'd like to collaborate on that, I would love to, love to talk.
Yeah, I agree. That would be huge, and would be very excited to collaborate as well. Thank you.
So there is, we have time for one last question by Luma, I think. So go ahead, Luma.
Okay, thank you. Yeah, this is Luma. And yeah, thank you for the presentation. And I have a couple questions. One is regarding the logic of the delta semantics. When you insert more data into both tables, you keep the existing answer side and join the delta side with the unchanged part of the existing data. How about we have the correlation between the two deltas that inserted into the two tables? If I think that might cause some missing answers. Yeah, if I don't miss anything. Yeah, this is my first question regarding the logic that for the example you gave. Another one is regarding for this delta semantics, whether you consider the index on the original table. And in that case, whether creating index is a good way or a bad way when you handling the answer set using this dynamic like incremental way, because sometimes the index access you can have like an insertion right in both tables, and if you have the index, that may kind of make this situation more complex, and the cost-based model, whether this model considered this extra like processing thing. Yeah, sorry, maybe a little too much information over here.
No, I think it's fine. So if I captured your first question correctly, I think you were concerned about the join between the two green parts and whether we missed them, but I think we already captured that in this slide also, right? So the final query is actually like 3 parts. The last part is that join between the two greens or the two deltas. Would that address your question?
Let me see. Okay, let me take a closer look.
Okay, so
okay, yeah. I think you're dealing with If that is covered, that's great. I think the second part you kind of take care of the inventory join the price delta. Oh, okay, yeah, okay. 3 union all. Okay, sorry, I missed the last part. Okay, that's good.
okay, thank you. The other one about the index, I think it's a good question. And definitely cost models start to become more complex if we want to factor in like index performances and so on. But in the current implementation, we don't factor in indexes, especially they are not very common in data lakes. And typically the use case here is in data lakes.
Okay, you have the application kind of restriction. Okay, thank you.
Okay, thanks a lot, Walla, for the presentation. Okay, so we are now to the last presentation of the day. So what I'm going to talk to you about is about optimizing common table expressions, a recent work that we have done in Hive. And now we are doing it with the help of Calcite. So let me start. Okay, so a few words about me. So as I said before, I'm Stamats Zabetakis. I work for Cloudera, and I'm a member of the query compiler team. And I'm mainly working on Apache Hive and Apache Calcite. So before I start, I would like to give an example about common table expressions, although I guess most of the people in this room understand directly what I'm talking about. So we have this SQL query that says that we have two tables. We have employees and departments, and we want to classify and return departments based on the average salary and classify them if they are greater than, let's say, average salary greater than 100K as high-cost departments, while if they are below 100K, they are low-cost departments. So I wrote the query like that on purpose because it's obvious that there is some commonality, some duplication. So we can see that we have a join here between employees and departments. We have an aggregation to compute the average salary, and this part of the query appears twice. So in practice, common table expressions appear very frequently in SQL queries. So they are either explicitly defined by the users, and in this case, they appear mostly using the with clause of SQL, or they can be implicitly present in the queries, in some cases obvious, like the query that I showed before, and in some cases impossible to see or even impossible to find out unless you perform transformations of the query. And actually, common table expressions is not very different than computation reuse or query caching. And we all know these problems that we employ caches everywhere. So finding and reducing repeated computations is crucial in every kind of use case. And in here, we can see that the more that we have data that increase, the cost becomes also greater. And when we are talking about Apache Hive, or in general about distributed systems, we have to deal with lots of data. So we are talking about petabytes and exabytes of data. So finding a way and exploiting common table expressions is crucial. Now, I will just to give you a quick overview about how the Hive planner works, so that we see how this new, let's say, common table expression optimization fits in. So as in every database system, we start by the SQL query that it gets from the parser, and it's transformed to an AST, so an abstract syntax tree that corresponds to the representation of the SQL query. Then we have what we could say logical optimizer, although logical and physical are not always exactly like they sound, but it's common to refer to them like that. So for the logical optimizations in Hive, we rely on Apache Calcite a lot. And actually, after we do the logical kind optimization and we obtain the optimized rel node, we have two ways to go to the physical plan and actually execute it. So the first way is to transform the rel node, the optimized plan, back into a SQL query. This may seem weird at first, but actually, if you think about it, it happens a lot. And many systems do it actually when they use Calcite. They take a rel node, they optimize it. For example, even if it is Postgres, you take a rel node, you optimize it using Calcite rules because they are quite powerful, and then you regenerate the SQL query, which is in some cases going to be more efficient. So this happens also in Hive. So we go back to the AST, which is not the SQL query, but it's the abstract syntax tree representation. And then we go back and produce a physical plan and do lots of kind of physical optimizations. The other part of the process is a bit more straightforward. So we have the logical plan, which is a Calcite plan. We have the Hive op converter, and we go back to the Hive physical plan that gets finally optimized and executed using TES. So I think it's a good moment also to say that those that think a Hive does MapReduce, it doesn't. It's been years that we don't do MapReduce, we do TES. So let's dig a bit more into the logical optimizer, because this is where we do the common table expressions, or at least this recent work about common table expressions. So as many systems, what happens first in the logical optimizer is we do subquery removal. So if queries contain subqueries, we extract them to the top level plan. And then as in other systems, we do query decorrelation. Then the third step in this logical optimization phase is actually the phase that has the the heavier and has the most rules, because here we are doing basically most of the very common optimizations like filter limit push down, simplifications, constant folding, constant reduction, branch pruning to eliminate redundant part of the plan, field trimming. So most of the most heaviest operations happen actually in the pre-join reordering phase. Of course, Hive does supports materialized view rewriting, and also for this we are using Calcite. So in Hive we are using the materialized view rule hierarchy that exists in Calcite, with some small specializations that are particular for Hive. After we get the views into the plan, we do the join ordering, which is quite an important phase, but actually we are not using that many rules. We are using 1 or 2 rules, and we are mainly relying on the, for those who are aware, lopt optimized join rule, which is a greedy way to pick joins, let's say. If I want to simplify extremely, every time you pick the best join and you continue like that. And the final phase so far is the post-join reordering, which is mostly about federation. So this is where all the federation rules comes into play. So if you have a JDBC database that you want to run queries over it, then this is where the JDBC rules are. If you have Druid as another storage engine, then this is where the Druid rules are. And this is actually the new thing that came in recently, like a few months ago. So we introduced a new phase that we do CT rewriting. And what exactly are we doing in this phase? So the first thing, as I said, is like, if we have the query, we want to find commonalities. We want to find common table expressions that are interesting. And after discussing with the team, with people, after checking various use cases, we realized that it's not easy to build an algorithm that will satisfy everyone. Like that will find, either will be too slow, either will not find the common table expressions that are needed, either it will be too heavy. So there is nothing that comes and makes everyone happy. And also another thing that we realized is that there are various proprietary tools that we may want to integrate with Hive, and we cannot really open source. So this is another way why we made this configurable. So we have a new interface, which is the common table expression suggester, and this is pretty simplistic. So it takes as an input a calcite plan, a rel node, and it produces 0 or more CTEs. It will detect the CTEs. And there are also rel nodes in this case. And this can be, the class can be plugged in by a Hive property that exists, that we introduced. And in order to show, actually to make some start, we also did an initial implementation that is very simplistic, but quite effective in the end. So what we did, we introduced what we say an identity suggester, which is basically tries to find identical subtrees in the plan. So it's basically a visitor, but not exactly, because actually Calcite has a rule that is not very well known, I guess, because it's also marked for removal. So, but this is actually, by extending this rule, you get kind of finding the common table expressions, the subtrees, automatically. So we did this with a few extensions, and we were able to make the suggester work very well, let's say. So if we go back to our example query, well, the rel node representation is a bit more complicated, but it's easy to see that there is the commonality. So again, we have the departments and the employees, the scan of the tables, and then we have the join between the two, and then the aggregation. So all this part and all this part is exactly the same. And when we get to the CT rewriting phase, this is exactly how the Hive plan looks like. So we plug in the rules, and we get back that this is a common table expression, and consider it to use it in the plan. So since this interface and logic is pluggable, we cannot really control if all the common table expressions or the suggestions will be useful, or if they will be able to be exploitable by Hive. So we have a bunch of Hive-specific, actually 2 Hive-specific filterings that happen to remove those that we don't need or those that are never going to be useful. And this is something that may appear in other systems. So if they don't support something, they may be able to employ some other prefiltering rules. And actually, now it's the most interesting part. So we have a class, we have some logic that does the detection, that finds the common table expressions, but it may give us 100, or it may give us 5, and actually we have to pick. So we need the cost-based decision. And thinking about it, like we said, like, okay, it's good because Hive already has materialized view logic, and it uses Calcite. So most of the code is already there. So what we did, actually, we said, like, okay, common table expressions is nothing more than views. So we'll model it as such. So we are saying we are actually getting the suggestions, the CTEs, and we are wrapping them around a relevant materialization, which is a materialized view. And then basically what we are doing is, like, we are saying, Hive, take these CTEs that are similar to materialized views and find those that improve the performance of the query. In that case, so the algorithms will take the suggestions and it will rewrite the initial plan using the CTEs that are modeled as materialized views, using the existing Hive cost model. So here we have the same plan, but we can see that everything was collapsed into the CTE suggestion, which is actually the materialized view, or the CTE. It's not really materialized, but it's modeled as materialized. And then we could even say that we are fine and we could go translating this to a physical plan directly. It is possible. But what we found missing, or what we found more appropriate, is that here we don't have an explicit producer-consumer relationship. So we don't know, actually, we don't see at first, we don't see the CTE. We just see a table that is called CTE suggestion. So the plan seems to miss some information. And also we don't see what is actually, is this part of the query that will create the CTE, or is this part of the query? So to solve this problem, we kind of use another operator that exists in Calcite, which is the spool operator. And the spool operator is actually used to mark the producer of the common table expression. So here, let's say we pick this to be the producer. So we'll expand it. Below, you have all the common table expressions that you have seen previously that was detected. And on top, we have a table spool. And now we know, for instance, if someone who is familiar with the plan can more or less understand that, okay, I'm reading this is the producer, and I'm pushing the results from here to a kind of table that is probably transient or transparent, which is called like that. And the other part of the plan is the consumer who is going to read from there. So we have a nice abstraction of how we can model common table expressions and translate it then to a physical plan.
Remark.
Sure.
We introduced the spool operator so that plans could be DAGs. Because a calcite plan always looks like a tree. But in this case, we want two different parts of the tree to reuse the same intermediate result. The spool is a way of, you can think of it as a way of joining together two trees.
Exactly, but because actually now DAGs, I mean, natural DAGs are not handled in calcite, the trick is to use the spool like that. And it is used like that for other use cases as well in calcite. So this mimics exactly, this mimics the DAG. So you have this, the spool that's sending the data somewhere. The edges, the DAG edges are not there, but they are implicit. And this is actually a good way to step into this part of transformation, because the physical part of Hive, the physical plan, is also a DAG. So it's rather easy to go from here to here by just connecting the spool with its consumer, the producer of the consumer. Okay, this is a bit more verbose, let's say. This is more Hive specific, so it might not be that easy to read, but we still see the join that is performed 2 times. We still see the aggregation. And okay, this is a bit like the exchange operator. So it's reduce sync, RS is for reduce sync. And actually, this is the part, let's say, if we didn't have any common table expressions, any sharing of work. This is the initial thing. So we want to see how things look like when we go with this optimization, with the city optimization. Let's see the first branch. So we want to have, we have the plan, and we have a new operator, which is the spool operator that Hive does not know about. So we need a way to go back into an AST. So we need a way to go back to a SQL query. Well, I guess you will not be surprised to see that the spool operator actually becomes a with clause. And what we have here becomes the name of the alias of the with clause. And so far, all the rest is already handled by Hive. So the query will be generated automatically by the converter, and we just have to plug in the logic for the with clause. And then the rest of the query will look like that. So the initial query that we have, after the optimized version will be equivalent to this part of the plan. And you may ask, why is this useful? I mean, you just wrapped everything in the with clause. So there is another feature that exists in Hive, a configuration that actually allows you to materialize the CTEs that are explicit with clauses based on a certain threshold. So by doing this part of the query that corresponds to the CTE will be materialized and will be fed to a temporary table. So FS stands for file sync operator. And we'll have the first part of the plan like that. And the next one, the rest of the plan, which is, I want to apply the halving clause. So the filter on salary, average salary greater than 100K and less than 100. So I will read from the temporary table, and I will do the rest of the processing. So I can see that I saved all this computation. And this can mean, this definitely means less resources, And it can also mean a better response time, less, and also less monetary cost. So this is what happens when we go through the AST. Now, when we go through directly from a rail node to a physical operator tree, things are a bit more easy, because as we said, the Hive plan is a DAG. So we just have to actually connect the edges. So there we have the computed common table expression, which is everything till the aggregation. And then we feed it just to the two consumers. So the one with average salary greater than 100K and the less than 100. And just putting the two alternatives side by side, the difference is more or less like that. For this query in particular, it may not be a huge difference, but still here we have to finish up all this phase before we start operating for the plan on the second phase. So we have to write all our results to a temporary table before starting the rest. While here, as soon as we have the results from the group by, we can send them to the network, and the rest of the processing can go on. So the first part is already committed. The second is a bit in progress. So it will be soon also finalized. Just to wrap up on what we have seen. So what we already knew, that common table expressions are present in every kind of SQL workload. We also know and have seen that the query cost can decrease dramatically if we take advantage of them. And cost can mean many things: money, resources, response time. Apache Hive utilizes Calcite for many optimizations, and now also for CTEs, for common table expressions. And the trick is actually to model CTEs as materialized views. This is not a completely new idea because it appeared in various research works. Then the next step is that we were able to model producers and consumers just by using existing operators, spools, and table scans that are already in Calcite. And we have also get a bonus of seeing how we can transform a spool into a physical plan with two different approaches, by transforming to SQL and by getting directly to a DAG plan. And last, the good news is that we didn't have to do almost any kind of extension to Calcite, although we may have some minor contributions, but all the primitives are already there. So all things can work out of the box. And with this idea here, you can do a similar common table expression work in another project, just by using materialized views from Calcite, planners, and everything is there. So yeah, some references for those who want to look up afterwards, and I will be happy to answer your questions if you have any.
Can I take the first question? I want to point out that CTE is a ambiguous term in the industry. When some people say CTE, they mean literally a with clause. So it's very confusing. What are the semantics of the with clause in Hive? I got to Google and discovered that BigQuery and F1 have different semantics than I believed, which is they are adamant that when you use a with clause, and if the query inside it is non-deterministic, that it's a repeatable result. So it may or may not cache the result and compute it and store it. But if, for example, you could use where random greater than 0.5, if you use that CTE twice in the same query, they guarantee you get the same answers. Is that your understanding of what CTE's with clause means in SQL?
I mean, with clause in Hive, I don't think we have repeatable. I don't think we have specified semantics other than that whatever is there has the same, you can have non-deterministic functions, and this follows mostly what Hive does with deterministic functions. So if it is executed per session, if it is executed per execution, per row. So this is, afterwards, I think it's mostly gets into what functions are used in the query. So the semantics go into.
Yeah, non-determinism can arise in things like, find the top 3 employees by salary, and you might get some ties. So it's not just non-deterministic functions. There's quite a few places of sources of non-determinism that the Google folks worry about an awful lot for some reason.
Thank you, Stamatis, for the talk. I was wondering when you have explained about the part about introducing the spool operator after the materialized view rewriting rules. I'm wondering how tightly coupled, I didn't get exactly how tightly coupled these 2 steps are, and if they are not, whether you think that's also kind of a possible extension there. So I'm wondering basically if you're in the same loop with the materialized view rewriting, or you are basically doing it separately, and where there are some opportunities for improvement there.
So that's a very good question, because actually we're thinking that we should maybe consider materialized views and CTEs at the same time. So we should consider them in a single phase. But this would have quite few side effects in existing use cases. So we decided to have them apart for now, but it's definitely a subject that came up. So first we will do view-based, MV-based, materialized view-based rewriting. We'll do the rest of the optimizations, and at the very end, we'll use a CTE that is going to use the materialized view rewriting logic, but only with CTEs. It will not consider materialized views, the existing materialized views. And it's basically the same code, let's say, more or less, code twice in different phases.
So all the plans you showed had Hive filter, Hive project, so not traditional logical, but you say that the code that exists for doing this would work also on the logical nodes?
Yeah. And actually, most of the Hive filter, Hive project, Hive join, I think it's just a naming. For most of the case, for most of the operators, you could replace Hive with logical and it will be the same thing. So they don't have exotic features, let's say, or other state. There are some historical reasons for why they are like that. Okay, so I think we are good with all the talks. Thanks everyone for coming or for joining remotely.